Okay, well, this video series is going to be the first part to acid-base chemistry. And I kind of wanted this video to be kind of like a quick prep before like a test or a quiz, kind of to help you understand things that you maybe didn't before. And so, like I said, it's part one. And in this, we're going to talk about these 4 points right here. We're going to talk about what an acid base is. We're going to talk about the pH scale. We're going to talk about how to get pH and pOH and some of the other math involved there. The last thing we're going to talk about how to determine the strength of an acid uh, or base without pH or pOH or anything like that. Okay, well, let's talk about the definitions of acids and bases. So, kind of what are acids and bases? Acid slash base. Bases. So, what are they? How do we define them? We're typically going to be using the Bronsted-Lowry definition of an acid and base. What that pretty much means is that an acid is going to be an H plus donator or an H plus giver. Okay, that makes our base something that's going to accept the H plus or it's going to gain it. Okay, so acid is H plus giver, base is a H plus gainer. Put gainer there. How does it work out in a reaction? How do we tell? So let's give a sample reaction here. Let's say that we have ammonium. So that's NH4 plus water. That's going to yield here NH3 plus H3O plus. And this is also called here hydronium. Okay, and just to be clear here, sometimes I might call this H plus a proton, okay? But that's just going to be the same thing. So I want you to pause the video here and kind of give your best shot to determine which one's an acid, which one's a base. Okay, so let me color code this real quick. I'm going to call an acid pink, and then let's call a base blue. So how do we determine what is what? I like to look at what a reactant becomes in a product. Sometimes it's a little bit harder to tell, but in this case, it's kind of easy. Well, we can say that NH4 has to become NH3. Well, how do we go from NH4 to NH3? We lost a proton, right? We lost hydrogen. Well, that means it has to be an acid, right? That's our definition of an acid. So this is an acid. We do the kind of same idea here for water, and we can say, hey, water, well, it gains that proton, right? It gains the hydrogen. So that means that this has to be then our base. Okay. Now, the question you might be asking is, well, hold on, we need to talk about conjugate bases, conjugate acids. What are those? I like to think about it as if we go in the reverse direction, if we're to flip the sign, okay, our arrow and go this direction, which one is now our acid in our base? We can see that, well, H3O plus or hydronium has to lose a hydrogen, so this is our acid, and NH3 plus has to gain a hydrogen, right? So that means that this one's going to be our base. And so when we go and unflip our reaction arrow, we can say that, hey, this is actually just going to be our conjugate base and conjugate acid. Okay, so let's move on now, talk about scale. Okay, the most common scale we'll be using is the pH scale. Okay, that's going to start at 0. It's going to end at 14. And pretty much, it's a scale of something like this. And so, right, if we're going to do some math here, right, 7 is going to be our middle. So what this means for us here, kind of how do we interpret this? Well, typically things that are from 0 all the way until 7 are acidic. And then things 7 to 14 are basic. And just to give you some examples, right? Things you might typically see in your textbook here, right? Typically at around 1-ish, we have here gastric juices. That's your stomach acid. Gastric juice. We also have things like coffee at like around 5. So around 5 is coffee. So for a basic side, your stuff like NH3 ammonia, right? That's typically around a 12. So this NH3. We also have bleach here at a 12.5. Okay, that's typically the most common scale we use, pH. The other scale we use from time to time is a pOH scale. And similarly to our pH scale, we're going to start from 0. We're going to go all the way until 14. And again, 7's the middle. Unlike pH though, we're actually going to say that 0 to 7 is basic. And we're going to say that 7 through 14 is acidic. Okay, and this kind of leads us into our kind of next point is, well, how do we calculate pH and pOH? And so this is the part where there's going to be a couple of formulas here. So bear with me while I kind of explain each formula and how we can obtain it, right? So talking about pH, that's the negative log of H plus. And so it's concentration. In the pOH, well, that's going to be the negative log of our OH, right, of our hydroxide. Do you see a pattern here? Do you see how the P here leads to, well, a negative log? That's no coincidence. When we see a P here, that's going to mean negative log. So pH, pOH is just negative log of whatever after it. Okay, we're also going to have another equation here, and that's going to be that pH is equal to 14 minus pOH. Okay, and then the last two equations that we'll use for now at least is actually going to be how to switch up these two equations. How do we get rid of log, pretty much? Right, and by doing so, we're going to get this equation here where 10 to the negative pH is equal to the concentration of H plus. And then here we'll also get that 10 to the negative pOH is equal to the concentration of OH minus. Okay, so let's try a practice problem then to see kind of how we can use these equations to help us out here. So let me just section us off here. Let's have a 0.0235 molarity solution of HCl. And let's try to figure out the pH, the pOH, the concentration of H plus, and also OH minus. So I want you to pause the video and try to figure out these four things here. Okay, so let's start with our math here. Well, we can say that if we have 0.0235 molarity of HCl, that means that we're going to have 0.0235 molarity of H plus. If you don't get that, we'll talk about that kind of in a next couple of kind of points. But just take my word for it now. Okay, that means that, hey, pH is just the negative log of that. So pH is equal to negative log of 0.0235. That means that pH is equal to 1.6289321. Right? It kind of goes on a little bit more. But remember, we want to keep our sig figs, right? So it looks like we want to round it here to our third place here. So right there. Okay, but I want you to keep in mind this whole number here. We're going to use it later. So then how do we get pOH? Well, we know that pH has to be equal to 14 minus pOH. We can rearrange that equation and say that then pOH is equal to 14 minus pH. So pOH is equal to 14 minus pH. Okay, so if you know what pH is, now we just plug it in. So we say pOH is equal to 14 minus 1.6289, all of that. And that's going to get us here 12.37. Keep up kind of sig figs here, right? We want to make sure that we kind of round it to here. But in this case, you know, it's fine to leave it like this. Okay, so the last two, how do we get then? The concentration of H plus, concentration of OH minus. Well, we kind of assumed what the concentration of H plus was, right? Just from our problem. But let's say we didn't have it. Let's say we only had pH. How do we get the concentration of H plus? Well, we would simply tend to the negative pH. So 10 to the negative 1.6289,321. That's going to be equal to the concentration of H plus. And that's going to be equal then to 0.0235. And we know that's true. Okay. Well, let's do the same thing then for POH, right? 10 to the negative 12.37. And remember, right, try to include as much decimal places as you can. Well, that's going to be equal to the concentration of OH minus. That's equal to 4.2553 times 10 to the negative 13. Forget the units. Okay, that's pretty much all the math here that we should know. So then let's move on to determining how strong or how weak of an acid or base that we have. So it comes down to determining the strengths of an acid or base. It comes down to its percent ionization. And what that is, it's pretty much how much of our reactant ionizes or breaks apart into ions. And that gets us to our constant for this unit, K. If we remember K from our equilibrium kind of chapter, we know it has to be our products over our reactants. So let's say I have this equation right here. Let's say I have an equation that's H2O, and that's in equilibrium with OH minus plus H plus. If we were to write the K expression, we would say that K is equal to the concentration of OH minus times the concentration of H plus, and we would say that's over divided by the concentration of H2O. But H2O is a pure liquid, right? So this essentially goes away, and we say that K is equal to OH minus times H plus. And don't forget we're taking the concentration of all that. So kind of what does this mean for us? Well, we can have a couple of more equations for this topic. We know that the Kw, so that's the ionization constant of water. Let me put a W down here. Kw has to be equal, it's going to be 1 times 10 to the negative 14 at 25 C. Okay, so at 25 degrees Celsius, water has this dissociation constant. So that means that we can often use Kw to kind of determine some of our concentrations if we don't know it. Okay, and if we were to use what we got on the previous problem with the HCl, we will see that the concentration of H plus, we do some manipulation. So if we say that Kw is equal to OH minus times H plus, and that's how you're trying to figure out the concentration of OH minus. So remember the last one, right? It was a 0.0235 molar solution of HCl. We can plug that in here and then divide Kw by concentration of H plus. If we were to do that, so let's set it up here. Divided by 0.0235, we would get 4.2553 times 10 to the negative 13, which is exactly what we got on the previous problem. Yeah, you see how it's the same? So kind of what does this mean for us? If K is kind of the percent ionization, why do we really care? We care because we can break up Kw to be equal actually to Ka times Kb. If you're wondering what this A and B is, well, it's acid and base. So the dissociation or the ionization constant for acid times dissociation constant for B is equal to Kw, and that Kw is still the same. That's still going to be 1 times 10 to the negative 14. So if you remember that K is equal to the percent ionization, that means how much of our substance dissociates or ionizes into two different things, or multiple different things. If we write a generic one for an acid, so let's say a generic acid, so let's say HX goes to H plus X minus, Well, think about it. The K expression then would be the concentration of H plus times the concentration of 8 of X minus over concentration of HX. What happens if our K is high? What happens if K is big? Well, that means that either our top part, our numerator has to be big, or our denominator has to be small. But both of them kind of mean the same thing. That means we have a lot of product. Okay, so if we're big, that means lots of product. And what's our product actually? Well, our product is the acid. So big K values, I should say Ka values here, mean we have lots of acid. So the bigger the Ka value is, the stronger the acid. We can do the same for Kb. Let's say we have some generic base, so let's call it XOH. With that H, that's going to give us here XOH2. Well, we can say the same thing. Kb is equal to concentration of XOH2 all over XOH times concentration of H plus. And again, we can do kind of the same thought process here, right? If Kb is big, that means that either our numerator has to be big or denominator has to be small. But either way, that means that we have more product than we have reactant, which means we have a stronger base. Okay. And now combining all that with the equation up top, with this equation right here, what we can say then, but hold on, if Kw is equal to Ka times Kb, well, we can manipulate this equation and say that Kw over Ka is equal to Kb. What happens then if Ka is a really big number? Let's say Ka, right, is really, really big. Let's use that Ka is equal to 5. Okay, Ka is equal to 5. So let's replace it here. If we were to do this math here, we get that Kb is a very, very small number. We'd say here that Kb equals to, that's going to be equal to 2 to the times 10 to the power negative 15. And again, right, if Ka or Kb is really big, it's a strong acid or base. So if Kb is really, really small, well, that means that this is a weak base. And then we kind of use the same logic here. That means that, hey, if Kb is really small, as we see in this problem here, right, it's really small. Well, look, our Ka value, right, that was 5. We have a really, really strong acid. Okay, and let's just try, just so you can see the math kind of works out. Let's say Ka now, 1 times 10 to the negative, let's say 10. Let's get Kb, right? So again, we're going to plug, instead of saying 5, we're going to plug Ka in for here. We're going to get that Kb is equal to 1 times 10 to the negative 4. And do you see how Kb is greater than Ka? So we know that this molecule here, whatever we're talking about here, is a better base than it is an acid. So that's going to be it for part 1 of this video, guys. If you liked it and you like the content, please give me a like, please comment, especially if you want something else or another material. That's going to be it for today. See you next time. Bye.